Okay, we're starting to talk today about Newton's laws of motion. And Isaac Newton was a very interesting guy. He did all kinds of stuff. He wrote about theology. He wrote a very interesting book on his view of Christ. I don't think we would recognize him today as a Christian per se. He saw some strange things in the person of Jesus, but he definitely believed in God, and he thought that Jesus was a historical person. He just had some interesting ways of describing Jesus' nature that would kind of lay him outside of Orthodox Christianity. But he wrote about it a lot. He did a lot in the field of physics. Obviously, we're studying today his laws of motion. He also had quite a bit to say about optics, and he invented calculus. So the entire division of mathematics called calculus was his, and he created it to be able to explain physics. So it wasn't created just to be created, it was created to answer a certain set of questions. And today we're looking at his three laws of motion. The first one is called the law of inertia. The law of inertia states that an object at rest remains at rest unless acted on by an outside force, and an object in motion remains in motion in the straight line path at a constant velocity unless acted on by an outside force. Some people call this the lazy law because things don't like to change, right? Something that is moving will keep moving, just like it is moving now, until something pushes on it. And something at rest will stay at rest until somebody pushes on it. So my mouse sitting here on the podium, if I don't touch it and I go home, I come back in the morning, it's going to be right there because nothing pushed it, right? And because an object at rest remains at rest. An object in motion remains in motion, so unless it's acted on by an outside force. So if I were to throw this little itsy-bitsy piece of eraser in the trash can and miss, the eraser remained in motion until it was acted on by an outside force. That being acted on was the fact that it ran into my desk because I missed the trash can. But it keeps going until something acts on it again. Okay, so the best example of that would be something in space. You know, if you're up in space and you throw a football and the guy catching the football misses, the football will keep going until Jesus recreates the universe, because the football will not be acted on by anything else, and it'll just keep flying, right? And at some point, it might hit a planet, it might hit an asteroid, it might get swallowed up by a sun, or Jesus might recreate the universe, and now the football's not there. But until that happens, it would keep moving, because nothing else would act on it. So the objects that are in motion remain in motion, objects at rest remain at rest until they're acted on. Now, the thing about the objects in motion remaining in motion, we don't see that as much here, because here there's always wind resistance, there's always friction. You roll a ball, it doesn't keep rolling for all eternity because it's going to hit something. But in an environment where there isn't anything that's going to act on it, it just keeps right on going. Okay? So this big rock remains at rest. And even though that woman is trying to push on it, her pushing on it is being counteracted by all the friction underneath the rock. So we don't have an unbalanced force on the rock yet. She would have to be significantly stronger to push this rock down the hill. But eventually, if she were to push on it with enough of an unbalanced force that it got moving, then it would keep going down the hill until something was able to act on it to make it stop. Okay, so inertia, objects at rest stay at rest, objects in motion stay in motion. And this slide wants to remain at rest. Come on, there you go. So this is a picture of our solar system taken from a long ways away, right? Not a picture actually, but a diagram. And this shows the 4 deep space probes that had been launched at the time that they drew this. We've actually had more deep space probes since then, but Voyager 1, Voyager 2, and then Pioneer 10 and 11 have all been launched and sent out from our solar system, out into the unknown cosmos. They've all crossed the orbit of Pluto and are out in what we call interstellar space. And they will keep traveling until they run into something or until God recreates the universe. And so they're just out and they're going and they're taking pictures and sending them back to us. And it takes longer and longer and longer for those pictures to make it back to the Earth, but they are still taking pictures way, way out there. It's kind of cool. They keep in motion. Inertia, you lose. I love that. This guy was in motion. He hit the wrong brake, and the front of the bike stopped, and the bike stopped, but he was in motion and he keeps going. So that's going to hurt a little bit. Okay? Inertia, your truck has brakes. The massive hulk of stone does not. So this guy was hauling a huge piece of rock in his trailer, and he stopped, and the truck stopped, and then the rock went through the container and into the back of his truck. Inertia. Things keep going. Okay, there you go. So the second law is the law of accelerated motion, and your text represents it, describes it in an arrangement of the equation that you don't see very often. I went ahead and put up here the way that your text describes it, but then I'm going to represent the equation to you in a more user-friendly way. So the second law is the law of accelerated motion. The acceleration of a system, if something is being accelerated, is directly proportional to the new force acting on the system and is inversely proportional to its mass. So what this means is that A, acceleration, equals F, directly proportional to the force, divided by M, inversely proportional to the mass. And that is true. You can say A equals F over M. The much more common way to express the equation that this law describes is F equals ma. Force equals mass times acceleration. I need a certain amount of force pushing on an object in order to get that object of a particular mass to accelerate at a particular rate of change. So F equals ma is the more common way of saying that. And so force is equal to mass times acceleration. We always use kilograms for mass. So if you get a mass in grams or a mass in pounds or a mass in tons, you have to convert to kilograms. And acceleration is always in meters per second squared. Remember, it's meters per second squared and not meters per second. Meters per second is a velocity. And we're talking about how much the velocity is changing. So it's how many meters per second it's going, different than the last second ago meters per second it was going, right? So meters per second squared is the unit of acceleration. So, and then there's a new unit here that you haven't seen before, that's the Newton. And the force is measured in newtons and obviously named after Newton, okay? He did not call them after himself. He didn't name that unit after himself. That would be kind of egotistical. But he described them, and he used kilogram meters per second squared. And then other scientists in the time around him said, hey, that whole kg ms squared unit is kind of cumbersome. How about we just rename it after you because you came up with this whole study? So it was in his lifetime that it was called newtons, but it was not by him. Named after him, it gets on. So force equals mass times acceleration. Some examples of this, bless your face. Okay, two dudes pulling on two rocks, and this dude has to pull very little to get little rock to accelerate across the table. Just a small amount of force, because the mass on this rock is very small. But this one has to pull quite harder to get this rock to move across the table. Much larger mass requires larger force for the same acceleration, okay? And apparently the young lady is fawning after the guy who can pull a big rock, not the guy who just pulls the little rock. She's not interested in the guy who pulls the little rock. Okay? Another example, this just lets you do some math with it. A sled dog pulls with a force of 100 newtons, and the sleigh weighs 50 kilograms. So then I could ask, What kind of acceleration does the sled produce? F equals ma. 100 equals 50 times the acceleration. So you don't have to be that good at math to see that the sled will accelerate at 2 meters per second squared, because the 100 newtons equals 50 times something, right? And 50 times 2 is 100. So there's that. And I just show you the math there. F equals ma. 100 equals 50 times something. Solve for the a, and that's 2 meters per second squared. Okay, so every second that sled will be traveling 2 meters per second faster than it was the second before. Here's another one. How hard does somebody have to push on their car? The car weighs 1,000 kilograms. If they're going to accelerate the car at 0.05 meters per second squared, meters per second, okay? So let's work that out. F equals ma. F equals 1,000 kilograms times I said 0.05 here, and I said 0.5 there. Oops, typo, my bad. 0.05 meters per second squared would make this 1,000 times 0.05 would actually be 50. So somebody would have to push with a force of 50 newtons, so roughly half as hard as the sled dog is pulling, to get their car to accelerate. Now, accelerating very, very slowly. The first second that they're pushing on it, it only goes 5 centimeters per second, right? The second that they're pushing on it, it goes 10 centimeters a second. Cars are heavy. It's hard to push. If it weren't going uphill, sure. So, F equals ma. Here's another one. F equals, you can't see the mouse. There's supposed to be a mouse there too. Oh, sad. Somehow that got cut off. But an elephant, big force required to move a big mass, but a mouse doesn't require as much force, little force to move a little mass. Okay, and now I think we're here. It's the third one. Okay, so the law of action-reaction. This one is usually the hardest for people to understand. You can comprehend inertia, you can comprehend acceleration. The idea of action-reaction is usually the hardest one to wrap your brain around. The law of action-reaction says that every force has an equal and opposite reaction. We've heard that said because that idea is used outside of physics. But to apply it to physics takes a little bit of work. So right now, I am standing on the floor. And my 200 pounds is directing a force because of gravity downward on the floor. Why don't I fall through the floor? Well, because the floor is pushing back up on me, right? I have a force downward because of my mass and gravity. The floor has a force upward on me. Those forces are in balance. What would happen if the floor were for some reason going to push harder on me than I push on the floor? All of a sudden I'd go flying up into the sky for a second, right? That doesn't happen because the forces are balanced. The floor only pushes up as hard as I push down on it. And then you would think, well, how does the floor know how hard to push? And how does the floor push? There's no muscles, right? This has to do with static events. An object that is sitting there in static relationship to something else, the forces are balanced. Now, the reason things move at all is because sometimes these forces become unbalanced, and then something moves. For example, when I walk. When I walk, why do I move forward? What's going on that pushes me forward as I walk around? Think about it. I'm walking, but why do I move when I walk? Why don't I just, like, moonwalk in one place? Right, but why do I move forward? Where is the force that pushes me forward? In my brain, no.
In your foot.
My foot, now pay attention when I walk, I am pushing backwards on the ground, right? My foot goes like this, right? I'm pushing backwards on the ground. The ground pushes forwards on me, right? Every action has an equal and opposite reaction. So I push backwards on the ground, but I am not strong enough to make the earth spin in that direction, right? Inertia. So even though I'm pushing backwards on the ground pushes forwards on me with the same amount of force. I am easier to move than the ground. So I am what moves. Even though I pushed on the ground is like, whatever. It pushes back on me with the same amount of force and makes me go forward. So the reason I walk forward is not because I am pushing myself forward. I am trying to push the ground back, and the ground says nope and pushes me forward, right? Which is why you fall when you wear roller skates, when you're first learning how those things work. Because you push backwards on the ground, and the ground doesn't push forward on you because the wheel absorbs the motion. And you go, whoo, and you're down. And so you figure out you have to push sideways on the wheel. And then now you get to push on the ground pushes on your wheel, pushes on you, and off you go, right? So the law of action reaction is the hardest one for people to think about usually because we don't think in third law ways. We experience the world differently, and we're not aware that it's the world pushing back on us that makes us walk forward. That's not immediately intuitive to you. So two people are pushing on each other, and they're wearing ice skates. And they will travel apart from each other at the same rate of speed. This person may feel like she's pushing harder on this person than this person is pushing harder on her, and maybe she is. But because they are in contact with each other, it's the total force that is going to be balanced. So force B pushing on person A is going to result in the same acceleration for A as person A pushing on person B with force A. They're going to be balanced, they're going to be equal, and the two ice skaters are going to slide apart at exactly the same speed. Okay? Because the forces will be balanced. Now that's assuming they weigh the same amount. But for this example, we can. Here's some other examples. Dude gets off a boat, and as he's chained to the boat, that's a bad idea. But I just noticed that. As he steps off the boat, he's going to push the boat backwards, and the boat's going to go backwards, and he's going to go forward, but only as much as the boat goes backwards. And so he may fall in the lake, basically is what's happening, because he's going to shove the boat backwards, even if he gets on a foot on the pier. The boat's going to be sliding backwards, and it'll yank him because he chained himself to the boat. I don't get it. But anyway, he's going to be wet in just a second. Here's the jet. The jet is pushing hot expelled gases out the back of the motor. And the backwards thrust out of the motor has an equal and opposite reaction of pushing the plane forward. So it's the backwards shooting of the exhaust that makes the plane go forward. Have you guys ever noticed when you fly that when the plane lands, some aircraft have just the air brakes that come up and make the wing like have a vertical wall and slow you down. Some aircraft, though, have scoops that slide around the motor, the engine, and blow the thrust forward. Have you ever seen those? Next time you land, because I assume people in Hawaii fly, next time you land, try to look at the area of the wing behind the engine. And oftentimes there are scoops that will slide down, and now the hot exhaust is actually blowing forward, and it's going to now thrust backwards and slow the plane down even more. So those are cool. A rocket, obviously the same idea, a blast of hot exhaust coming down the bottom. The equal and opposite reaction will push the rocket upward. And then here, if you have a sprinkler, one of these sprinklers that spins itself around on a ball bearing, it's because the water flying out these two things causes a torsion, causes motion on the sprinkler and spins it around. Okay? So all of those are examples of third law things. When you shoot a gun, we live in Hawaii where guns are almost illegal. But if you've ever shot a gun before, you'll notice that there's a little bit of a kick when you shoot a gun, right? And the faster the bullet goes, the more of a kick that you get. And actually what's happening is you are experiencing every bit as much force in the recoil of the gun as the bullet carries. So when you shoot a gun, the target receives the same amount of energy that your hand does. Why doesn't it kill the person who shoots the gun just like it kills the person who gets hit with the bullet? Well, because we're carrying it at different amounts of mass, right? F equals ma. Same amount of force, but in a lot more mass, just a small amount of acceleration. Whole lot of force, itsy bitsy bit of mass, a lot of acceleration. So the bullet is going a lot faster. Funny story, I went shooting with a friend in Arizona, and he had a rifle that's called a 45-170, which means 45 caliber bullet with a whole lot of black powder behind the 45 caliber bullet, 170 grains of black powder. That rifle has about an 800-yard effective range. 8 football fields away, you hit a target. It's an incredible rifle. But it kicks like a mule. I mean, it hurts to shoot that gun. And the first time we went shooting, he has this big rubber cushion that he puts on the butt of the gun. So when you hold it, the rubber cushion absorbs the shock. He had taken it off, and he hands it to me. I didn't know the thing existed. He's like, hey, you take the first couple shots. I'm like, oh, cool. Set up this target. I squeezed off a couple of rounds, and after firing 3 rounds, bruised shoulder, and I'm like, oh, I can't do it anymore. I'm gonna have to take a break. And I'm looking around for something to put on my shoulder, and I'm like, do you have a pillow or this hurts? And he said, oh, and he pulls out of his truck this big rubber butt guard. And he slides it on. He's like, oh, there you go. And he starts shooting. I'm like, oh, thanks, Jerry. So yeah. Anyway, every action has an equal and opposite reaction. Where's my mouse? Where's my mouse? Oh, there you are. Okay. So, just more examples. Engines thrust backwards, the plane goes that way. Air gets forced down by the wings, the plane goes that way. So, force pairs, okay? Last thing to talk about is friction. Okay, so last thing to talk about is friction. Friction is a force that opposes motion. If there is no motion, then there is no friction. As soon as there's motion, there's friction. Friction always opposes motion. So as you start to move something, you ever notice that, let's say you're dragging something heavy. It takes more work on your part to get some heavy thing sliding than it does to keep it sliding once it's sliding. So friction always resists something moving. Then once it starts to move, the friction is still there, but it's not as strong. And the strength of it depends on the force holding the 2 objects that are going to slide across each other together and the kind of material they are. So there's friction right now between my shoe and the floor. As long as I'm walking, there's friction, right? And you can turn the force of friction into useful motion. The only reason you can walk is because you have friction. If you had frictionless shoes, you would not be able to walk. You'd go like this and fall down, right? Friction is what keeps you on something. As long as you're walking, as long as there's motion, there's friction. A larger person will have more friction between themselves and the ground than a smaller person will have. So if we were to measure the force of friction in my shoes as I'm walking around right now, the force of friction on my shoes in the floor is smaller than if Janine were also pacing around, right? So I'm a bigger person than Janine. And the other thing that comes into play with friction is not just how hard they're being forced together, but the type of material, which is why different kinds of shoes produce different amounts of traction. That's why you wear cleats, because it provides a huge amount of friction into the ground and keeps you from sliding around, right? You wouldn't want to go wrestle with somebody wearing roller skates. That would be dumb, because you wouldn't be able to get a good footing. Your feet would slip out from underneath you. So the kind of materials that are pushing against each other and how hard they're pushing against each other determines friction. Interestingly, it has nothing to do with surface area. So I weigh roughly 200 pounds. If I get all of my weight on the front half of 1 foot, then, and I were to somehow try to walk on the front half of 1 foot, there is the same amount of friction on that little area as when I stand on both of my feet and walk. Same total amount of friction. Surface area doesn't matter. The mass of the force between the two objects and the kind of material they are. So the kind of material they are comes into a term called the coefficient of friction. We represent that with the lowercase mu. That's the lowercase Greek letter m. And it looks like a U with a long front leg. Okay? And that is the letter mu. That is the coefficient of friction. And that has to do with the kind of material it is. So you can look up the value for mu for different materials. And then the normal force is the force pushing two objects together. I'm pushing on the floor with a certain amount of force because of gravity. The normal force is the floor pushing back upon me. It's the third law of air force to mass. So normal force times the coefficient of friction for the material gives you the value for the amount of friction that there is between those two objects. So you can experience friction, just a small amount of force, you can rub your hands together, and they do get a little bit warm, and you can feel the sliding, right? If you push harder on your two hands, then it gets hotter faster because you're creating more friction. And you can experience that too. You can't experience the normal force thing. I guess actually you could if you were to like put something slippery. Then you'd have to push really hard to get heat and friction building up because the slipperiness goes into play there too. Okay? So that's the idea of friction. Here's some pictures for you. You have a mass. You're pushing on it to try to get the mass to slide this way. The friction will be a third force pair, and it always opposes motion. So you're sliding the box this way, friction is going to say no, go that way. And so it always subtracts from the acceleration that you actually get from the force. Okay? And just another diagram of a mass of an object. You apply a force in one direction, the force of friction goes in the opposite direction. And here's the mass, the weight of the object sitting down on a surface. The normal force, that is the pair to the weight. We use the value of the normal force and the material that this is to calculate how big that force of friction is. Okay? And it always, like I said, it always opposes motion. So if there is no motion, then there is no friction. And there's usually different values for sliding motion and rolling motion. That's why we put cars on wheels, not just shoving them along the ground, right? Rolling friction is always a lot smaller than sliding friction. And again, it has nothing to do with surface area. So the friction that this boat is experiencing in the water only has to do with the mass of the boat and the coefficient of friction of water as it slides past the boat. A small hull of the same mass boat would have the same coefficient of friction. A large hull with the same mass of a boat would have the same coefficient of friction. It's just mass and the value of the materials coefficient that controls it, okay? That's why they like hovercrafts for trying to get big things across bodies of water, because the hovercraft doesn't touch the ground. And so its friction is a lot less. It only has the friction of the air that it's pushing away from itself, not the friction of touching the ground of the water. Okay, so that's why we tend to put cars on wheels, not slide them in. That's why hovercrafts move faster than boats, because there's a lot less friction involved. Okay, friction is also a valuable thing. We use friction a lot. It's why you can walk. Friction is what makes a match head light, amongst many, many, many other things. We use friction positively as well. Here is a cool video of friction being used to weld something, where they don't have to use anything to heat it up, to heat two parts up other than friction. Some guy at work, I'm sure he got in trouble for filming what he does. Okay, two parts. They spin one. They stick two parts together. It gets super, super hot because of friction. And then when they stop the motion, which we'll have in just a moment here, the parts have been welded together. It's red hot. It cools. And now those two parts have been welded together. Isn't that cool? So, there we go. So that's friction welding. Kind of neat. So we use friction for lots of things. Any questions about the Newton's 3 laws or friction that I can clarify for you? Alrighty then, we will start to play with this with labs tomorrow.
Understand.